Swayam Prabha. Digital India. Educated India.
We are looking at VAB being integrated. If I had taken VAC being integrated, I should have started from what angle? This is 60, this is 30, so I should have started from 90. 90 to 150. That's what I should have integrated. But I should have written VAC as Vm sin omega t minus 30. Because it is lagging behind VAN by 30 degrees. So if I am integrating VAB, I better write plus 30 because it is leading VAN. Whereas if I write VAC, I better write omega t minus 30 because it is lagging behind by 30 degrees. So when you choose the limits and when you write a specific voltage, please be aware and sure what you are writing. What you are taking as the reference 0 and how do you specify each of the voltage waveform with reference to that 0. You have to be really thorough with that. So for that, at least for me, phasor diagram help. Always. I always draw the phasor diagrams to understand which is leading, which is lagging. So that helps me really. And if I have to, for example, look at the phase shift between these two, very easy to see. It is 60 degrees. Very easy. So when you draw the phasor diagram, it becomes much simpler normally. Right? Is this clear? If you try to now integrate this, this will give simply 3 Vm by pi. Where Vm is the line voltage peak. For half wave rectifier, it would have given you 3 Vm by 2 pi. So this is 3 Vm by pi, Vm being line voltage peak again. Vm is line voltage peak. So, if I have all of them as diodes, again, this is my alpha equal to 0 point. Later on when I put the controlled rectifier, I will always take this as alpha equal to 0 degree point because that is where my D1 is taking over naturally. If I want diode to take over naturally, at what point it is getting forward biased? That's what I have to check. So, I am going to get alpha equal to 0 normally as the point again same as what we saw in the half wave rectifier. It is exactly 30 degree away from the 0 crossing point of VAN. Before we progress to fully controlled 3-phase rectifier, let us try to compare slightly the single phase case and the 3-phase case. In single phase case, when we drew the voltage waveform, it was something like this. It would go from the peak until 0 like this. This is how it was. In single phase case when I had just diode, full bridge diode rectifier which is uncontrolled. So this is single phase diode bridge rectifier output, right? So this was omega t and this was pi, this was 2 pi and this was 0. That's how it was. And the peak was like Vm and the minimum value was 0. So the ripple in the voltage could go from 0 to Vm completely. Right? Uncontrolled I'm talking about. If it is controlled, it can go to negative also. That's what we talked about. So here the ripple happens to be just 0 to Vm, which is quite a large value. So if I apply this to, for example, a DC motor, although I will pacify the DC motor by telling it that I am applying 2 Vm by pi average voltage, the motor will groan. because you are giving it oscillating voltage. The current will oscillate. If the current oscillates, I am definitely going to have the torque oscillating. I hope you understand. If the torque oscillates, the speed will also oscillate. The shaft will vibrate. So there will be a huge amount of ripple in the current, ripple in the torque, ripple in the speed. Everything will lead to huge amount of vibration and noise. So single phase rectifiers are hardly ever used in a DC motor drive of very large capacity because of this reason. If it is a large capacity drive, the vibrations normally will not be tolerated so much. If there is a small crack in the shaft, in a paper mill or textile mill or in a, tire producing industry, they are not going to tolerate even small vibrations. The thread will go all haywire. You will not buy such a cloth which comes out of the textile industry which is having all vibrations. So single phase rectifiers are known to have a huge amount of voltage ripples, current ripples, torque ripples, speed ripples, vibrations, noise and so on. So they are not generally utilized for large capacity DC motor drives. Maybe 5 kilowatt, 2 kilowatt. It's all right because it may not be a very crucial industry. As simple as that. But if it is a large motor, for example, you think about a train, right? Madras still, one of the suburban train service runs with single phase rectifier, controlled rectifier, but they put a large capacitor and so on. That's how they manage. But whenever you are thinking of large capacity drives, if on the other hand, if you look at the three phase, just now we drew it. So it started from about 30-degree point, right? The voltage waveform started from about 30-degree point and it went up to 90. So it was something like this. This is how it was. 6 such pulses within one single cycle because every pulse corresponded to 60 degrees, right? So I'm going to have essentially pulses like this. So this is the peak. And the entire thing is 60 degree, which means this is 30 degree and this will be another 30 degree. On either side there is 30 degree from the peak. The peak corresponds to 90 degrees, which is sine 90, which is 1. On one side it will be sine 60, the other side it will be sine 120. How much is sine 60? Root 3 by 2. So the ripple only will be from root 3 by 2 to 1 times Vm. Root 3 by 2 is 86.6%. So the ripple is going to be from 86.6% to 100%. Whereas the ripple here is from 0% to 100%. What I mean by ripple is what is the maximum and minimum, the difference between the two, that is called as the ripple that is present in any DC voltage. If it is from a battery, it will be steady. The ripple is literally 0. There is no ripple at all. Whereas if it is from a rectifier, there is bound to be ripple. And when I have ripple, the minimum the ripple is, it will be closely, emulating or copying a DC voltage. So I would like to have as much as possible, a steady DC and at least close to a steady DC. So this is essentially the output of a 3-phase diode bridge rectifier. So here ripple is equal to Vm, ripple voltage. So here I am going to have ripple voltage equal to 100% minus 86.6% of Vm. So in that sense, I will have, my 3-phase diode bridge rectifier almost copying a DC voltage pretty much. So this is definitely much more suitable for running a DC motor drive as compared to what I would do with a single phase rectifier. So generally this is always used for less than 10 kilowatt rated motor. It is never used rather for beyond 10 kilowatt. Whereas three phase may be used in many cases where I have very large capacity drives like 500 kilowatt, right, 700 kilowatt. Such motors are also run with the help of three phase rectifier, right. Now let us go over to three phase controlled, rather fully controlled bridge rectifier. So obviously I am going to use 6 thyristors. All of them will be thyristors. If I use 3 thyristors and 3 diodes, then I will call them as semi-controlled. We'll look at that as well, but first we'll start off with fully controlled. So I'm going to have a circuit somewhat like this. So this is A phase, this is B phase, and this is C phase. So this is VAN, VBN, VCN, and I'm going to call this as T1, T3, T5 and T4. You always add 3, that's it, T6 or subtract 3. If I have 1, I will have 4 at the bottom. If I have 3 at the top, 6 at the bottom, and 5 at the top, 2 at the bottom, right. So this is going to be the configuration of a fully controlled bridge rectifier 3 phase. Obviously here also the current will flow from up to down, and I will like to have a control over the output voltage, so I might like to vary the firing angle. I would request you guys to now spread yourself. We'll continue with this in the next class.